I welcome you all for this presentation. In this presentation, we are going to discuss about analysis of algorithms. This is the overview of this presentation. Here we are going to discuss about the types of analysis, how do we compare algorithms, then ideal solutions, then asymptotic analysis, rate of growth. Again, we are revisiting the asymptotic notations followed by some examples. In the last presentation, we discussed about asymptotic notations. There we discussed about 5 notations. Here we are going to analyze the algorithm. So analysis in the sense case by case analysis. By analyzing case by case, we are having 3 categories of analysis. First one is the worst case analysis. Worst case analysis in the sense it provides an upper bound on the running time. That means we doesn't mean that here upper bound in the sense it is big O or small O. Likewise don't mean that. This case analysis is different from that of asymptotic notations. Asymptotic notations are for representing some functions in a small way. That is for that only we are having asymptotic analysis. This analysis part, case analysis, is different from that of notations. But here also this case provides an upper bound on the running time only, but notation is different from that of this analysis. And this worst case analysis provides an absolute guarantee that the algorithm would not run longer no matter what the inputs are. That is worst case in the sense what is the worst possibility. So most of the day we consider the worst case analysis only. Why we are considering means at the max this is the performance like that. So only we are considering the worst case. Best case is it provides a lower bound on running time. So here also it doesn't mean that the lower bound, the omega notation don't mean that this best case analysis provides the lower bound on running time. Here input is 1 for which the algorithm runs first, but for defining, representing the lower bound on the running time, we are having the omega notation. But best case is entirely different, that notation is different. And here we know the relationship between this lower bound and upper bound. Always lower bound less than or equal to running time, less than or equal to upper bound. Suppose we are having one, always the functions must belongs to any one of the classes only. In the last presentation we have seen 1, then log n, then we are having root n, n, then n log n we are having, then n square, n cube, then up to then 2 power n, then 3 power n, then up to n power n. So here this suppose if you take the average bound, here means this side we are calling it as a lower bound. From this to this say n to 1 we are calling it as a lower bound, then n to this n power n we are calling it as a upper bound. So it provides a best case provides the lower bound on running time. And average bound, it provides a prediction about the running time. So average time that only best fits, but most of the time this average case doesn't fit for any of the algorithm. But worst case and best case we consider. Average case it just we are predicting the running time. So here we are assuming that the input is random. In that way only we are finding about the average case. Next, how we are comparing the algorithms. So we need to define some objective measures. That is whether we need to compare with respect to the execution time. If you compare with respect to the execution time, what happens means it is dependent on a particular computer, because my computer works in a different way. Other computer works in, if we have the same configuration means also different computers work in a different execution time. So comparing just the execution time is not good enough, because times are specific to a particular computer. Next measure is count the number of statements executed. It is also not good. Why not good means, if all the 61 members I am giving a program to write means everyone's lines of code is different. So each and every individual programmer style is different. And whatever the language you are using, whether you are using C or C++ or Python or Java, anything, it differs. So counting the number of statements executed, that comparison is also not good. So what is good? These two are compare execution times, comparing number of statements, lines of code, or the programming language, those things are not good. Then what is good? That we need to know. So here the ideal solution is we have to express running time as a function of the input size n, that is f of n, and here we have to compare different functions corresponding to the running times. So such an analysis is independent of the machine time, programming style, etc. So only here we are just using the running time for comparison purpose. So here we are having the asymptotic analysis. We know what is asymptotic notation, then how to analyze the asymptotic analysis we have to know. So to compare two algorithms with the running times f of n and g of n, we need a rough measure that characterizes how fast the function grows. Here, what is the rate of growth with respect to different function, that we have to look into. That is, here we are compare the functions in the limit, that is asymptotically. That is, for large values of n, we are just comparing it. That is the asymptotic analysis. Here rate of growth, in the sense we consider one example. We are considering the cost of elephants and cost of goldfish. Suppose if the cost of the elephant is high, means what we are telling, the cost is approximately equal to the cost of the elephant. The just cost of goldfish, we are negligible. It is negligible because it is small, so it is negligible. Compared to elephant's cost, it is small, so it is negligible. Likewise, only while writing the running time analysis also we have to look into. For that only we have this real-time example. So the lower order terms in a function are relatively insignificant for large n, because it is asymptotically we are performing the analysis. So the lower order functions are relatively insignificant. So this higher order functions, n power 4 is there, means it is approximately equal to n power 4, because this is the higher order. Others are lower order, they are negligible or insignificant. So here we say that n power 4 plus 100 n square plus 10 n plus 50 and n power 4 have the same rate of growth. So here we are telling that both this one and this have the same rate of growth. Likewise, cost of elephants plus cost of goldfish and cost of elephants, both are having the same rate of growth. That is the meaning. Here constant in the sense the order of 1, that is whatever it may be, whether it is order of 50, some value 50 or 100, anything we have to, whatever the constant we are having, we have to represent it with order of only, whether it is 50 or 100, any value. If you have to represent with respect to 1 only, we have to mean it that it is a constant. That is, it requires constant number of operations not depending on the input data size. Here we are telling that we require only constant number of operations. That is the meaning. Next is logarithmic order of log n. That is the number of operations proportional to log n, where n is the size of the input data. And linear means it is order of n. That is the number of operations proportional to the input data size. Quadratic means order of n square. That is the number of operations proportional to the square of the size of the input data, n square. And cubic means number of operation proportional to the cube of the size of the input data. Then we are having the exponential. Here exponential number of operation, that is, it is fast growing. Compared to other things, it is a fast growing. Then 2 power n, k power n, n factorial, many things are there. So different complexity and different notations we are having. Most of the time we are telling it as big O. Y means it is the upper bound. At most the upper bound we are telling. So only most of the time we are writing it as big O, but omega and theta notation also, if possible, we can write it. No issue in that. But the upper bounds only we are writing it as big O. Then coming to the asymptotic notations, already in the last presentation we discussed about asymptotic notations. There we discussed about 5 notations, 3 big notations and 2 little notations. Here we are going to discuss about the notations with respect to the example. Here big O notation, asymptotic, it is less than, it represents less than, that is f of n equal to order of g of n implies that f of n is less than or equal to c into g of n. So if you take this example 16n cube plus 45n square plus 12n, that is f of n value we are having, then g of n we are having n cube, then how we are writing f of n is equal to big O of n cube. How we are writing means, we have to prove that f of n, that is here this 16n cube plus 45n square plus 12n, it must be less than or equal to some c into n cube. So here already we are having 16 n cube. So here what we need to do is 16 n cube plus some value, some 45 n square is there. So you just give 5 n cube, then 12 n cube. Likewise, if you give means the value becomes more. And always we have to satisfy the condition that this LHS left hand side is less than or equal to the right hand side. This we have to prove it for all values of n greater than or equal to 1. This condition we have to satisfy. So if this condition is satisfied, then we can write that f of n equal to big O of n cube. Similarly, for the next function 34n minus 40 and g of n is n, here also we can write here 50 and 1. So how you can write 50 less than or equal to dash 1. So here we can write 50, at least 50 means also it's satisfied. So 50 into n. So it is equal, 50 equal to 50. So we can write f of n equal to big O of n. But if you write 50 less than or equal to 49 into 1 means this condition is false. Here we can't write it like this. Always we have to write, we have to satisfy the condition. That is more important. Then coming to the omega notation, it is greater than. This big O is less than or equal to omega is greater than. For that you just work out these examples and try it. Whether you are getting a C value, constant value that satisfies everything or not, you have to check it. And if it satisfies, then we can write. So for the first one also we can write omega of, because big O is the upper bound and omega is the lower bound. So we can write it. Then coming to the theta, big theta notation, it is equality. When we are calling it as equal in this sense, this f of n, C1 g of n less than or equal to f of n less than or equal to C2 g of n. So here g of n is n square only, here also n square only, both sides same. Some lesser value here you have to give for the constant C1 and for the C2 you have to give some higher value. That is the only difference. Other than that, if both are same only. So only here we are having the asymptotic equality. So f of n equal to theta of g of n implies that f of n equal g of n. Here meaning is not the value that n square, that term is equal there. But f of n we are having n cube. But this C1 g of n is less than or equal to f of n. That is f of n is less than or equal to C2 g of n. So the equality exists between this g of n, left hand side g of n and the right hand side g of n. So only here we are mentioning it as equal. Then I have given you some examples. Fa of n equal to 30 n plus 8 is order of n, or big O of n. It is at most roughly proportional to n. At most means it is the maximum at most. And fb of n equal to n square plus 1 is order of n square, or the big O of n square. That is here it is at most roughly proportional to n square. So in general, any big O of n square function is faster growing than any n function. N in the sense, if you see 1, 2, 3, likewise only it goes on. But if you take n square, this is 2 power, that is 1 square, 2 square, 3 square, 4 square, means here 1, 4, 9, 16. It is going fast compared to this n. So only here in general, any big O of n square function is faster growing than any big O of n function. Always the right hand side is the upper bound. They are going fast only compared to this left hand side. Then you see this one on any graph. We can go to the right. A faster growing function eventually becomes larger. So n square, n it is going like this only. N square means it is growing fast. This side it is going. So this n square is growing faster compared to n. Here I have given you some example. N power 4 plus 100 n square plus 10 n plus 50 is big O of n power 4. Is it possible to write omega of n power 4? That is also possible. Because this is the upper bound, this is the lower bound. But we have to check whether it is possible to write theta of n power 4. That condition, whether it is satisfying, means we can write theta of n power 4 also. Then 10 n cube plus 2 n square plus big O of n cube. This also you can write it as omega of n cube also. N cube minus n square is big O of n cube. This also you can write it as omega of n cube for the lower bound case. Then coming to the constants, 10, it is big O of 1. This one, anyway, whatever the number given here, we have to write it as, for the constant, it is 1 only. Then here we are having big O of n, what are the functions look like? Big O of n square, what are the functions look like? Big O of n log n, how it looks like, order of 1, whatever the constant value we are getting, here we can write. That is, the big O of g of n is the set of functions with a smaller or same order of growth as that of g of n. So for one notation itself, different functions are coming into one group. That is the meaning here. See here I have given you some more examples. In the free time you try to solve it. 2 power n square is big O of n cube. So how we are writing? We have to check f of n less than or equal to c into g of n. This condition has to be satisfied. Likewise for all the problems you try it and check it so that we can prove that this function equal to order of another function. Next is proof, right, of the type of thing. Show that 30n plus 8 is big O of n. Here what you have to do is the same principle only you have to apply. There exists c and n naught, then 30n plus 8 less than or equal to, big O means always less than or equal to c into f of n, g of n, for all n greater than n naught. So here you have to substitute some values and find out, and you have to prove it that this is left hand side is less than or equal to right hand side. So we can prove that 30n plus 8 is order of n. Likewise, if it is given that 30n plus 8 is omega of big omega of n means also you can prove it. You have to change the constant values only. So here you see 30n plus 8 is in less than n anywhere, n greater than 0. So here even if it is less than 31n everywhere, but it is less than 31n everywhere to the right of n equal to 8. So it is growing this side. Here we have plotted n value 30n plus 8. Suppose we are cn equal to 31n, means it is coming this side. So big O means it is an upper bound. So it is above it. So we can prove like this by drawing also we can prove it. So only here 30n plus 8 belongs to big O of n. It is the upper bound. Another one thing you have to notice, there is no uniqueness, that is no unique set of values for n naught and c in proving the asymptotic bound. So you can, whatever the constants you need, you can write. So in proving this value, each one of you will take different constant values. So for n naught and c, different values we can substitute. But what is our objective? Ultimately, the condition has to be satisfied. That is the main thing. So we must find some constants c and n naught that satisfy the asymptotic notation relationship. That alone is important. Other than that, any constants you can try it. The condition we have to satisfy. So there is no unique set of values for n naught and c. Another some examples I have given. This see here 100n plus y, it is not equivalent to omega of n square. Y means you have here the proof is there. N cannot be smaller than a constant. So this, if such condition exists, means at that time we can't tell that this is equal to omega of n square. So you must be very careful enough, just looking into, don't write the answer. You have to work it out and write the answer, because some contradictory cases are also there. So this is another example. So in the free time you try to work out all those examples. Then you check the answers for this also. Here I have given some pair of functions and I ask you to find the relationship is correct or not. So you please go through it. Try to work out it and find out whether it is correct or not, and check the answer. Why also, the justification part is also required. So in summary, we have discussed about the types of analysis, that is worst case, best case and average case. Then how do we compare algorithms, that also we discussed. Then what is the ideal solution for comparison, that is the running time. Then we discuss about the asymptotic analysis, rate of growth, and we discuss some examples related to the asymptotic notations. Thank you.